Okay, today we will discuss about this memory interfacing, how you interface memory with the microprocessor. So before starting with the interfacing, let us revise some basic concepts, what a memory is and how it is basically designed. So if you have studied in your digital electronics course, a flip-flop or a latch is basically used as a basic storage device for storing a single bit information. Okay, so flip-flop or latch is a device which is used to store single bit information. Okay, which is basically called as memory cell. So it can store either logic 0 or logic 1. Okay, one bit at a time. So logic 1 and 0, that these are some voltage levels. Okay, so it can store either a high voltage or a low voltage, so which is called as logic 0 or logic 1. Now all these memories, they are basically designed based on this flip-flops. If you talk about these SRAM, static RAMs, of course. Okay, in dynamic RAMs there are some more different categories of RAMs. You may use some other element as a memory cell, but most of these static RAMs, they are designed using the flip-flops. Okay, so they are more fast. In fact, they are more costly as well, but they are more fast as compared to the dynamic RAMs. So if you see what is a flip-flop or a latch, so when you study the basic latch in your digital electronics course, so we say that a SR latch is basically designed using a cross-coupled NAND gates or NOR gates. Okay, so I'm not going to detail of these latches and flip-flops, but just to introduce, because they will be used in designing the memories and how interfacing is done. Okay, so basic latch is you have two NOR gates, or you can use NAND gates also, and the output of this is given as input to this, and the output of this is given as input to this. So this cross-coupled NOR gate, this forms a basic SR latch. Okay, so you have two inputs S and R, and you have two outputs Q and Q bar, which are the complementary of each other, right? And you know what is the truth table for this. Okay, so when S and R, set and reset, these are called as set and reset, and you have Q as output. So if you apply 1 to S and zeros to a low to high pulse to the set input and a high to low pulse on the reset input, your output is set, Q is set to 1. Okay, similarly if you apply 0 0 after this, so at 0 0 there is no change, it means the output remains at 1. Okay, similarly if you now apply 0 and if you make R as 1, it is reset, its output is 0. Okay, and similarly when it is 0 0 after 0 1, there will be no change, the output will remain at 0. Okay, and there is an intermediate state that when we apply 1 1, so that we generally avoid. Okay, so this is a basic latch. Okay, so you can store 1 bit information in its output, that is Q, by applying a proper input to R and S. Okay, so if you want to set this flip-flop, or if you want to store 1, so you must apply 1 to S and logic 0 to R. Okay, if you want to reset the flip-flop, you have to apply a logic 1 at R and logic 0 at S. But before you change that, suppose if you have applied logic 1 to S and logic 0 to R, your flip-flop is set. But before you change, before you apply 1 to R, this S should has gone to 0. Okay, otherwise it can be intermediate state, it is already at 1. So if you do not make it 0 and you apply or as 1, it will go into the intermediate state. Okay, so once you set it, you apply a logic 1, and the second input must be at logic 0. Okay, so before you reset it, this S should have gone to 0 from 1, then you apply a logic 1 at R, the flip-flop will be reset, it will store now 0. Okay, this is what is the basic flip-flop. So the output is basically controlled by the input. Okay, so depending upon the combination of the logic signals at the input, you get a change in the output. Okay, so you can set or reset the flip-flop. This is what is called as our latch. Okay, and then there is a clocked flip-flop. So in the clocked flip-flop, what we do basically, so you have a clock pulse which is used to control the change in the output. Of course, the output is changed by the combination that you apply at S and R, but at what time the output will change, that is decided by the clock signal. Okay, so it is like this. Okay. So you already know these concepts. I am just giving an overview because it will be helpful. This is basic SR latch. Okay, so you can set or reset this flip-flop latch by applying a proper combination of logic signals at the input. Okay, now if you want to control the timing that when this output should change, so that can be done by using a clock pulse. Okay, so in that case what you do, you have a clock pulse, and that clock pulse is basically ANDed. It is connected with the AND gate. Okay, so we have CP clock, so this R and S, now they are not given directly to the latch, in fact. Okay, so your S and R, they are given through this AND gate, which is called as a pulse steering circuit. Okay, so you connect this R as another input to this AND gate, and now this will be given as input to this. So this is R basically not here, now it is here. Okay, similarly you have one more AND gate. The output of that is connected to S. So S is applied as input to this AND gate, and this clock pulse is also applied as input to this. Okay, so the clock pulse, the clock signal that you are going, it is given as input to both the AND gates. Okay, and of course S and R, they will be one of the inputs to these AND gates. Okay, now what will happen if you have used a AND gate? So for AND gate, your output will be only when both the inputs are at 1. Okay, it means if we have a clock pulse like this, so when this clock pulse is 0, okay, by the time, for the time when this clock pulse is 0, the output of both the AND gates is 0. So for SR latch, if your input is 0 0, there is no change in the output. Okay, that you have seen from the truth table. Okay, and if the clock pulse is high, for this time when the clock signal is high, so this clock pulse, the input of this clock at this pin is 1. So the second input, it can be 0, it can be 1, anything. Okay, so if it is 0, output will be 0. If it is 1, output will be 1. Okay, it means whatever is the logic at S or R, that is simply transferred to this input to this latch during the time when the clock pulse is high. Okay, and when the clock pulse is at logic 0, so all the inputs to this flip-flop latch, they are 0 0. As a result, there is no change in the output. It means to set or reset this flip-flop, what you must have, the clock pulse must be high. Okay, so during that time only this latch will respond to the changes in input. So when the clock goes from logic 1 to logic 0, there is no change in this output. Okay, so you can store the information in the latch or in this flip-flop now, which is clocked flip-flop, only during the positive level of this pulse. Okay, and there's one more thing, that as long as this flip-flop this clock remains at logic 1, so in between this, as many times R and S will change, your output will change. Okay, so it means that, so there are two things, one is the input and one is a clock. So the clock basically decides the timing when the output is going to be changed. Okay, and how the output is going to be changed, that depends upon the combination of the inputs. Okay, so as long, so suppose you have let us suppose you have a clock signal. This is a clock, this is one time period, then another time period, similarly another time period, and so on. Okay, and I take some arbitrary or random input. Okay, so you take some input which is this, so what should be the output? Okay, or in fact the flip-flop that we use in these memories, that is called as a D flip-flop. So D flip-flop is nothing but your, it is generated from the SR flip-flop. Okay, so if you, in D flip-flop you have just one input and one output. Of course two outputs are there, Q and Q bar, but the input is only one, so D input. So in fact SR latch is basically converted to into D flip-flop when you apply S as one input and the second input your D in, it is one is given to S, and then you take the complement of this, you give it to R. Okay, this is how you convert a SR flip-flop into a D flip-flop. So in D flip-flop you have only one input, but that same input is given to S and R. Of course in one case it is given in the inverted form. Okay, so you have Q and Q bar here. So if it is 1 0, it means if your input is 1, what will be output? Your flip-flop will be set, because it is 1 0, set to set. Okay, if your input is 0, so this will be 0 1, S is 0, R is 1, your output will be 0. So your output simply follows the input. So if the input data is 1, output is 1. If the input is 0, output is 0. This is what is happening in the D flip-flop. Okay, so you have D flip-flop. Now along with this you have a clock signal here. Okay, so this flip-flop, the output of the flip-flop, that is Q, will just follow the input. Okay, but how it will follow the output, that will depend upon this clock pulse. So I have taken this as a clock, and this is my input to the flip-flop D in. Now see what should be the output. If you plot the output Q, so what will be the output? So at this point when the flip-flop, it goes from logic 0 to logic 1. Okay, it means now by this time, by the time this clock remains at logic 1, your flip-flop output will change depending upon the what input you are applying at the input. So this is your D input. Okay, so at the starting, when your clock pulse goes high, your input is 0, so your output will also be 0. Okay, Still at this time the clock pulse is high and the input has gone from 0 to 1, your output will also go from 0 to 1. Okay, so this output will basically simply follow this input. Okay, it will trace this output, but for that time only for which the clock period is high. So by this time up to this point your clock signal is high. It means up to this point your output will simply follow the input. So Q will change according to D. Now at this point your clock signal goes from 1 to 0. It means now the output cannot change. Okay, so the output will remain constant till the next clock pulse comes, right? Although you can see here, if you see here, when the clock signal has gone from 1 to logic 1 to 0, so after some time this input also goes from 1 to 0. Okay, but this change in input will not make any change in the output because the clock pulse is not at logic 1. Okay, and similarly when the next pulse comes here, so your input is 0 at this time. Now it means now Q will follow D, so it will go from 1 to 0. Okay, it will remain 0 at this time. It goes from 0, input goes from 0 to 1, your output also go 0 to 1 because the clock is again at logic 1, so it will go up to this time. Okay, now at this point of time your clock pulse again goes from 1 to 0, so the output will be remain constant till your next pulse comes. And you can see in between there are many transitions. The input goes from 1 to 0, then from 0 to 1, but this will not make any change in the output because the clock is at logic 0. Okay, and so on, right? This is how you can plot the output. This is what is called as level triggered flip-flop. Okay, so such a kind of flip-flop we call it as level triggered. Okay, because it responds to the level. So as long as the level is high at logic 1, the output will change according to the change in the inputs, and it goes from level high to level low, logic 1 to logic 0, there will be no change in the output. Okay, and then there are some edge triggered flip-flops like you studied. Maybe it's a master slave flip-flop or it is a edge triggered D flip-flop. So in that case what happens, the output changes only at a particular transition when the clock goes from logic 0 to logic 1, not for the entire level. Okay, so if we have a level triggered flip-flop, suppose, and if you plot the output for this, what should be the output? So at this point when the clock goes from level 0 to logic 0 to logic 1, your output will change. Okay, so since the input is 0 at this point of time, it means your output remain 0. So this will remain 0 for the entire clock period till the next clock pulse comes. Okay, this is what is edge triggering. So it activates the circuits only at a particular edge. So if it is a positive edge triggered, whenever the transition is from logic 0 to logic 1, your output will change. Okay, if it is a negative edge triggered, so when the pulse goes from logic 1 to logic 0, your output will change. Okay, now see at this time when the next pulse comes, so your output will again follow the input. So input is again at logic 0, it means your output will remain at logic 0. Okay, next transition will be taken place at this time when the clock again goes from 0 to 1. Now at this time your input is at logic 1, so your output will be at logic 1. Okay, so this is for edge triggered flip-flop, this output. So here the transitions are made at the rising or the falling edge of the pulse only, not for the entire level. Okay, but this structure is basically a level triggered. So for edge triggered you have different designs. I'm not going to that. So you understand now what is a flip-flop. Okay, so flip-flop is basically a storage device which can be used to store a single bit information. That is, it can store either logic 0 or logic 1. Okay, So, and you can set and reset it by applying an input and with a clock signal. Of course, we call it as enable pin now in the flip-flops. Okay, so you have enable pin and you have input. So when the enable pin is high and you apply some input, so that output goes to the that input goes to the output basically, right? Now see, so you have flip-flop or latch as a storage, basic storage element. Okay, D flip-flop in fact. So you have input, you have enable pin, you have output Q. So this output Q changes according to this input. Okay, when this enable pin is high, right? So I'm talking about this level triggered. This is not as triggered basically. Okay, so as long as your enable pin is at logic 1, so whatever is the input that comes at the output. Okay, and then sometime what we do, we use, so this we generally D as input and Q as output. So this is D in, I can write it as D in, this I can write as D output. So this is my enable pin. Okay, so many times what happens is that to control this change in the output or to make unnecessary changes in the, because see, as long as your input is high, as long as your enable pin is set at logic 1, if there's any change in the input D, that will come at output. Okay, so in order to avoid such a situation, we generally use tri-state buffers. Okay, so what is a tri-state buffer? So we have a circuit like this. So D, this is Q as output. This is connected to a tri-state buffer, which is controlled by now your read signal. And similarly, input is connected to a, sorry, input is connected to a tri-state buffer, which is enabled by basically a write signal. So this is D in, and of course we have along with this a enable as input pin. Okay, now what is this symbol? This symbol is basically for tri-state logic devices, or you call it as tri-state buffer. Okay, so tri-state buffer is basically a logic device which has 3 logic states. Okay, as the name itself suggests, tri-state. So normally in the digital circuits we say we have 2 states, either logic 0 or logic 1. Okay, but the tri-state devices, they have 3 states, that is logic 0, logic 1, and one is called as high impedance state. Okay, and all the tri-state devices, they have, how they are different from the normal digital devices, they have a enable pin. Okay, so when this enable pin is active, they perform as normal logic devices, and when this enable pin is disabled, that device goes into the high impedance state. Okay, so high impedance state means it is basically disconnected from the system, as if it is not there. Okay, like for example, if you say inverter or a NOT gate, so you have an inverter, this is inverter, this is what we represent as inverter. So whatever apply at input, so the output is nothing but the complement of the input. Okay, but if you say tri-state inverter, so in that case you will have an enable pin also. Okay, So this enable pin, it can be active high, it can be active low. So if you use a bubble here, it means it is active low pin. If you are not using any bubble, like in this case, it is active high pin. So this is the same inverter that we are using here. Okay, the purpose of this is to provide a output which is the complement of input, but this circuit or this device has to be enabled before it functions. Okay, it means if your enable is high, if I talk about this particular component, so when the enable pin is high, so whatever is the at input, it will give its output as the complement of that. So if it is 0 here, it will give 1 here. If it is 1 here, it will give 0 here. So it will function as a normal inverter or a NOT gate. Okay, but if the enable pin goes to 0, it means this device goes into the high impedance state. So high impedance state means it is basically now disconnected from the system. Okay, it will not respond to any input. Okay, similarly this is active low enable. So when it is at logic 0, when enable is at logic 0, then only this inverter will perform. Okay, this is what is a tri-state buffer. So you say one more extra you can see pin is included, which is used to enable or disable the device, right? So generally when any device, when it operates in the logic, in any normal logic or 0 or logic 1, so it you can say drives some current, it takes some current from the system. Okay, but when it goes into the high impedance state, so there is no current that is drawn from the system by that device. That is what is the meaning of high impedance state. Okay, so it is disconnected from the system basically. So if this is my basic D latch or a D flip-flop, so if I include tri-state buffers for the input and output, what will happen now? The input and output cannot change. Okay, suppose your enable pin is high, because I have taken it as active low pin. So if my enable pin is at logic 1, and if you apply, if in this case, suppose if your enable pin is at logic 1, and if you apply some input here, okay, so of course that will simply come at the output because it is a D latch, D flip-flop. Okay, so the output will trace simply the input for the time when the enable pin is high. Enable is nothing but basically clock now. Okay, so clock is denoted as enable. But if you see at this diagram, if the enable is high, okay, and if you apply some input at D in, okay, so will that input come to this? Yeah, of course, that will come to the output only when you enable this tri-state buffer. That means you apply a logic 0 to this tri-state buffer, then only this input will come here, then from here it will go here. Okay, so that is why right control signal is connected the input, because when you want to write some information into this latch, which is now a basic memory element, so right pin must be activated. Okay, so if you send a high to low pulse on this pin, so this tri-state buffer will simply pass the input to the output. Okay, and similarly if you want to read some data from the latch, for that the read signal must activate this output buffer. Okay, although the signal is present here. Okay, the signal is present here, but to read this output you must activate this tri-state buffer by sending a low pulse to this. Okay, so in between, if there is some change in the input and due to that state output changes, of course that does not matter because it does not appear at the output unless and until your this read signal is activated. Okay, so this is what is a basic single bit storage device which is called as HR flip-flop. Now with this much background, you can combine the flip-flops in a sequence and you can generate various registers which are used to store many bits. Okay, so resistor is basically now a combination of resistor, which is combination of flip-flops. Okay, so in a register you can store more than one bit now, because a flip-flop is used to store a single bit. So if you combine many flip-flops, you can get a register, and if you combine many registers, you can get a memory. Okay, that is how it is. So as a simple example, suppose I take a 4-bit register which is used to store 4 bits. It means you must have 4 flip-flops. Okay, now you know already what we have in a one flip-flop. So in a one flip-flop, so you have one D flip-flop, D as input, Q as output, and then there is an enable pin, of course. And this input is basically controlled by some buffer. Output is also connected through a buffer. Okay, and enable pin must be high. This is one flip-flop. Similarly, you can have one more such flip-flop, the same structure. So you have input, okay, output. This is output buffer. Similarly, one more flip-flop, input with a buffer, output with another buffer. Okay, so one more I will take 4 bits. So 4 flip-flops are there. So this is input, this is output. Okay, so all of them have their own enable signals, enable pins, you can say. Okay, now this structure is used to read or write 4-bit information at a time, because I'm using 4 flip-flops. Okay, and how it will be done. Okay, so this flip-flop can store 1 bit, this will store another bit, this will store another bit, and so on. Okay, so first thing is that if you want to store 4 bit at a time, or if you want to read 4 bit at a time, all the flip-flops, they must be activated simultaneously. Okay, it means what has to be done, the enable pins of all these flip-flop, that must be tied together, and you must have a master control here, single enable pin. Okay, so whenever this pin goes high, 0 to 1, all the flip-flops, they get enabled at the same time. Okay, because all these pins now I have tied them together and connected to a single pin at the output, which is enable pin, first thing. Okay, similarly, now input, we have 4 inputs. It means one input will go to this flip-flop, second input will go to this flip-flop, third input to this, fourth input to the last one. Okay, so we have one input here. Let us suppose I write it as I0 for this. The input for this is I1. The input for this flip-flop is I2, and for this flip-flop my input is I3. Okay, and see, again, whenever you want to write some information into this register, it means all these tri-state buffers at the input, they must be activated at the same time. Okay, so what you have to do, you have to again tie all these buffers together. So this input buffer will be connected to this input buffer will be further connected to this, and this will be connected with this. Okay, so all these 4 inputs, they are again tied together, so you have one single input. Okay, so buffer control, right? Or in fact, this is not input now. Input is different. Input is I0, I1, I2, I3, but those inputs, they are not going directly to the D flip-flop. They are basically interfaced using tri-state buffers, and this tri-state buffer will be controlled by your write signal. Okay, so what will happen? If there is some data on the inputs, suppose I have 1 here, I1, it is suppose 0, I2 is 0, I3 is 1, okay, and you want to store this 4 bits into this memory, this register in fact. So what you have to do, you have to simply send a control signal on the right pin, okay. So when you send a control signal that is high to low pulse, what will happen? All these tri-state buffers, they will be activated at the same time, okay. So when they gets activated, whatever is the data at the input of these flip-flops, that will come to their output, okay. So this 1 will come here. Similarly, if it is for the second flip-flop input is 0, so this 0 will go at the output and so on, okay. So to store now this information 1 0 0 1, right? If you want to read some information from this, if you want to read these 4 bits, what you have to do? You have to activate now this output buffer, okay, for all the flip-flops. So for that, it means again you have to connect them together. These must be tied together with a single control signal, that is read, okay. So although the information is available at these pins at the output of flip-flops, but this information is not available at the output of this tri-state buffer, okay. So you have output pins here also. So this is output, suppose O1. The second output is here. This is output 2. Third output is here. This diagram became somehow more congested. Sorry for that. So this is output 4. So 0, 1, 2, 3, 4. These are my output pins. Okay. But the data will appear at the output pins from this flip-flop only when you activate this tri-state buffer. So these all the 4 tri-state buffers, they must be activated simultaneously. So that is done by the control signal read. So whenever you apply a signal which goes from 1 to 0, okay, so all the 4 buffers, they will get activated, and whatever is the output, what it will store in the flip-flop, that would come on the output lines. Okay, so from the output lines now you can connect it to the databus. Okay, now one more thing is there. So you have 4-bit register, it means you have 4 flip-flops. So you have 4 inputs, you have 4 outputs, you have 1 enable pin, 1 read pin, and 1 write pin. So when you activate this enable pin, all the flip-flops, they get enabled at the same time. And when you send a control signal maybe for write, it means whatever is the data or the input, that will be stored in the flip-flops because it activates your tri-state input buffers. Okay. Now since we have 4 inputs and 4 outputs, it means how many data, if you have databus, so how many lines will be required in the databus? You need 4 lines. So you may have, say, it is okay, D0, D1, D2, D3. This is databus. Okay. Now these input outputs, they must be connected with this databus, of course, because the data will come through databus from this register, or it will go into this register through databus anyhow, to and fro, whatever it is. Okay, so how that is done? So how you should connect the databus with these input and output lines? Okay, so for that, what we have to do, it means all the 4 lines of all the 4 wires for the databus, they must be connected with the 4 input lines. Okay, this must have a connection with, suppose, this input, I take it as this one. So I1, this should also be connected with the second bus. Your I2, this should also be connected with the third. Similarly, I3, the fourth input, it has to be connected with this. Okay, so all the 4 lines, 4 inputs of these registers, they are connected with the 4 data lines of the databus. Now since we have one data, we do not have 2 separate databus for taking the data into the register or for taking data from the register. Okay, so databus is single, a single group of lines, so they can be used to store the data or to read the data from the memory or to write the data into the memory. Okay, it means either at a time the input signal or the input lines, they must be connected to the databus, or the outputs, they must be connected to the databus. But anyhow, similarly, the input or the four inputs of this resistor, they will be connected with the databus, and at the same time, all the four outputs, they should also be connected with the databus. So output 1, output 2, output 3, and output 4, they are connected with the databus. I will just show like this. Suppose you have this is some memory. Okay, so you have four data lines for this case. Okay, so if you want to read some information from this memory, that has to come through databus, it will go to the processor. If you want to write some information into the memory, that will come again to the same databus and go inside the memory. Okay, it means, but inside this memory, we have what? We have registers now. So you have, suppose I'm taking a 4-bit register, so we have 4 flip-flops. Okay, so you have 4 input lines, 4 output lines for reading, input lines for writing. Okay, so what I'm saying is that these 4 lines, they are connected with the databus. Okay, because whenever it is a write operation, so the data will come from this databus, it will go on the input lines, and then when you assert this control signal write, it will be placed in the flip-flops. Okay, if it is a memory read operation, so in that case again the data will come through the same 4 lines. Okay, it means these 4 lines must also be connected to this databus. Okay, so this is basically parallel connection, you can say now. Okay, so if it is a memory read operation, so the processor will send a control signal read, all the flip-flops will get activated, so the data is placed on the databus, it will come inside the processor. Okay, so but at a time, see, at a time either the processor will read the data or it will write the data. Okay, it means either the data will come from these 4 inputs which are connected with the databus. This data from, in fact, the data from the databus will be placed on these inputs, or if it is a memory read operation, the data on the output will basically come on the databus. Okay, so you have the same databus, so inputs and outputs both are connected with the same bus parallelly. Okay, so this is what is the basic resistor, so which are basically designed by combining the flip-flops. So you can extend it now. Okay, if you have such 8 flip-flops, so you can have a 8-bit register, so you can store 1 byte of information, right? Again, the process is same, you have to connect all the enable pins of all the flip-flops together. Similarly, the input buffers must be tied together, connected with the write control signal, and the output buffers must be connected with the read control signal. Okay, now how it is basically enabled. Now, see, this is for one register. Okay, so for one register it is okay. Once you send some enable signal here, so the all the flip-flops, they are enabled simultaneously. Okay, so whatever is the data, it comes on the databus, or whatever is the data at the input, it goes into the flip-flops. Now suppose you have let us suppose we have now memory having 4 registers, each capable of storing 8 bits of information. Okay, so 4 into 8 register, you can say. Okay, or 4 into 8 memory, you can say, not register, in fact 4 into 8 bit register. It means we have 4 registers. Now you know already what is a resistor. So inside the resistor we have flip-flops. Okay, so you have 8 bit 4 resistors. So this is resistor R0, this is R1, this is R2, this is my R3. Okay, so you have to arrange now these resistors in a sequence so that at a time you can either read or write the information from one of these. So either you can read the information from R0 or you can write the information into R0 and so on. Okay, so this is what now becomes a memory. Okay, so it's a 4-byte memory. Now how you control this, because see at the input you have just one pin. At the, if you see a memory chip, it is also in the form of integrated circuits, so you have dedicated pins on that for read, for write, for enabling and so on. Okay, so how you select one resistor at a time, what should be the logic for that? You can see from this is one 4-bit resistor. If I might have another same 4-bit resistor, it means 4 flip-flops with the same inputs, same outputs, then enable everything as that. Okay, but the input for this will be of course different, right? The output of this is different. The enable for this has to be different. Okay, similarly you have read and write signals, control signals, read and write. Okay, so what I am saying is that I have 2 resistors, each of 4 bit. Okay, so this is one 4-bit resistor, this is another 4-bit resistor. Okay, so what I want to do is I want to access the information at a time from one of this. It means I want to read either the contents of this 4 bits register, or I want to read the contents of this 4-bit register. So what I should do is, so what I should do is that it means either I have to enable this at a time, or I have to enable this register at a time. These both should not be enabled simultaneously. Okay, these both registers should not be enabled simultaneously. So if you want to select this register, it means, now see, for this 4-bit register you have an enable pin. Okay, so this enable pin must be high, so I can set for that time this enable as 0. So if I make it as high, this as 0, it means this register is basically disabled. You cannot read or write information from this because its input is at logic 0. Okay, so how you do that? So that is done basically by the address decoder. Okay, so you have a decoding circuit now for that. It means what you can do in this case, you can simply have a circuit like this. Suppose 1:2 decoder. It means you have one input, you can generate 2 outputs from this. Okay, so this is output 1, this is output 2. So this is input. So input can be 0, it can be 1. So what I can do is that if my input is 0, this pin will go high or logic 1. If my input is 1, the second input will go high. Okay, so like this, either I can enable this register or I can enable this register at the same time. Okay, so we will continue with this in the next class.